Hi everyone, welcome to the post-contest discussion of the Codeforces Round 985. I am Abhinav Kumar and this is TLE Eliminators. So let's get started with our first problem, which is problem A set. Okay, so you are given a positive integer k and a set S of all integers from L to R. Okay, and you can perform the following two-step operation any number of times, possibly zero. First, choose a number x from the set such that there are at least k multiples of x in the set, including x. Then remove x from the set. Note that nothing else is removed. Find the maximum possible number of operations that can be performed. So basically what the problem says is that you are given three integers L, R, and K. Okay, let's say you are given 392, the first test case. Okay, so you are given three integers. One is L, one is R, one is K. Okay, then you are said that you have a set S containing all the integers in the range from L to R. That means in this test case, from 3 to 9, all the integers are present in the set. So this set would be 3, 4, 5, 6, 7, 8, 9. Like this. Okay. After that, you are given a K. So here K is equal to 2. It means that in every operation. Okay, so you need to find the maximum number of operations you can perform. And what the operation is that you can pick up an integer x. Let's say you picked up 4. Okay, let's say you picked x is equal to 4. Okay, from the set, you would pick one of the integers from the set. And then the x should be such that there are at least k multiples of x present in the set. So if you look at the set, how many multiples of 4 are present? Okay, we can see that for 4, 3 is not a multiple of 4. 4 is a multiple of 4. 5 is not. 6 is not. 7 is not. Then we have 8, which is a multiple of 4. 9 is not. So for 4, we can see that we have 4 and 8. There are two numbers in the set which are a multiple of 4. Okay, so for 4, for x equal to 4, there are two numbers which are multiple of 4. Okay, and since we know that this 2 is greater than equal to k, which is 2, okay, so we can pick this 4. Okay, so we'll pick this 4, and what would happen? This 4 would get removed from the set. Okay, so this 4 gets removed from our set. Okay, this is one operation. Now, the next operation, again, we need to repeat this step in the remaining set. We need to select an integer x such that it has at least k multiples present in the set, and then remove that integer. Okay, let's say we picked, next we pick x equal to 3. Okay, so we can see for 3, 3 is a multiple, 6 is a multiple, 9 is a multiple. So there are three multiples of 3, and 3 is greater than equal to 2. So yes, 3 can be picked. So we'll pick 3 and we'll remove 3. Now, if you look, let's say we pick 5. Okay, can we take x equal to 5? Okay, if we take x equal to 5, we can see for 5, we have this 5, which is one of the multiple. And then all the remaining numbers are not a multiple of 5. Okay, so we only have one multiple of 5. And since 1 is less than 2, okay, it's not greater than equal to k, then we'll say that we cannot pick this 5. Same for any number in the set. If you pick any number, there is only one multiple. Okay, so now we cannot perform any more operations. So the maximum number of operations that we can perform in this particular set was 1 and 2, two operations. So our final answer for this would be 2. Okay, we can perform two operations. Okay, as you can see in the first test case, our answer was 2. Okay, in a similar fashion, you need to solve. So I hope the problem is clear to you, what we need to do. Now, how can you solve this problem? Okay, let's look at the constraint. We have L and R up till 10 to the power 9. Okay, so we need to find the solution. Like we cannot go in order of L or order of R. Okay, we cannot one by one check every integer like that. We need to find some solution in some optimized way, maybe in some order of 1 or order of log n time. Directly we need to calculate. Okay, so let's see what we need to do. We have a range from L to R. We have all the numbers from L to R. Okay, basically it means if let's say this range was 3 to 12. Okay, that means we would have all the numbers 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so our set would be something like that. Starting from L, till R all the numbers. Okay. Now, what would be the most optimal way to perform the operations? Okay, now every operation we know. First of all, if you look at this set, what all in what all numbers, how would you decide that for what all numbers we can apply an operation? Okay, we are given some k. Let's say here k was 3. Okay, so for 3, what all would be the multiples of 3? It would be 3, then 6, then 9, then 12. Okay, so multiples of 3 would be these. So how many multiples of 3 are existing in this set? 3, 6, 9, 12. There are 4. Okay. For 4, how many multiples are there? It's 4, 8, and 12. There are 3 multiples. So 4 is also okay. 3 is greater than 3. For 5, we have 5, then 10. Then there would be 15, which is greater than R. So 15 is not present. Only 2 multiples, 5 and 10. So there are only 2 multiples, which is less than K. So for 5, we cannot perform the operation. Now, since for 5 we cannot perform the operation, for 6 also, after 6 there 6 after 6 there would be 12, and then 18 is not present. So only 2 multiples. So for that also we cannot apply. For 7 also. All the greater numbers, obviously you can see we would not be able to apply the operation. So for k equal to 3, we would say that for 3 and 4 we can apply the operation. For the remaining numbers we are not able to apply the operation. Okay, what if instead of 3 we were given k equal to 2? Okay, let's suppose we were given k equal to 2 instead of 3. Then what would our case be? For 3 there is 3, 6, 9 and 12. Okay, 4 multiples. Obviously greater than 2. It's okay. For 4 also we have 4, 8, 12, 3 multiples, which is also okay. For 5, we have 5 and 10, 2 multiples. Now for k equal to 2, this is also okay. Okay, so all these would be okay. For 6 also, we have 6 and 12, 2 multiples. That is okay. Now for 7, we have, after 7, there should be 14, which is not present. So only one multiple is present, which is less than k. So for this, we would have a cross that we cannot perform an operation with k equal to 7. For 8, 9, 10, all the remaining, there would be cross. Okay, so first thing you can notice that uh, it would be a pattern like this only. Up till something we like less than equal to some value, there would be till some value we can perform the operation, and after that we cannot perform the operation. Okay. Okay, now let's suppose k is given 2 only. So what would be the most optimal way? Okay, so for these numbers, after removing some number, whether if for these numbers we cannot perform an operation, that means there are the number of multiples present in the set is less than k. So if after removing some number, definitely this number of multiples are not going to increase. So it would remain less than k only. So after some operation, this condition is not going to change. The cross would remain cross only. Now, what about the tick? Okay, so there are 4 numbers on which we could have performed the operation. So first, on which number would we perform the operation? Okay, so if we are performing first on the bigger number, then it may happen that for this 3, this 6 was a multiple, which is not a multiple now. So it may create a problem that before for 3 we were able to perform the operation, now maybe we are not able to perform. In this case, after removing 6 also, there would still be 3 multiples and we can't perform the operation. But what is the best case? Best case is remove the smaller number first, because by removing this, there is no number before that whose multiple this 3 would be. So it is not hampering any of the numbers from becoming not eligible now. So what we would do, we would greedily start. We would remove this 3. Okay, now for 4, still they are 1, 2, 3 multiples. So we would remove this 4. Then for 5, still we have 1 and 2 multiples. We will remove 5. Then we will remove 6. Okay, so basically, if initially there were 4 numbers for which we can perform the operations, then finally those would be the 4 numbers that would be removed, and our answer would be 4 only. Okay, so okay, this is the first thing. Now, how can we find this? What is the, how many numbers? Okay, from the start till where is that place where we need to stop? Okay, one way is, you can see this is like a predicate function, 1, 1, 1 and 0, 0. So you can apply binary search. Okay, that's one way. Or you can, maybe if you look carefully, you can just directly find which would be the first number, or which would be this number after which we cannot perform an operation. So if you look at this 12, Okay, we need to find a number for which like there should be k multiples. Okay, so if k was 2, that means 12 by 2 it is 6. So 6 would be the number for which 6 would be one multiple, 12 would be the second multiple. Now all the numbers greater than that, their second multiple would lie ahead of 12. So for them, we would not be able to perform the operation. So the greatest number for which we can perform the operation, okay, so we can say that the greatest number for which we can perform operation would be, okay, the last value, if the last value is r, then I would say r by k would be the greatest number for which we can perform the operation, r by k. Okay, and what if r was still 13 here? Okay, if r was still 13 here, then 13 by 2, okay, 13 by 2 would be 6.5. So we'll take the floor value 6, because for 7 we would need 14, okay, which is greater than 13. So 7 would still be the cross. So the greatest number for which we can perform the operation, it would be r by k, the floor value of r by k. Okay, that you can observe that if r by k is 6.5, that means before 6.5 till 6 we can perform the operation, after that we cannot perform the operation. Okay, so the floor of r by k gives the greatest number for which we can perform the operation. So how many numbers would we have from l up till r by k? Okay, so this value would be r by k, the starting value would be l. So from l till r by k, how many numbers exist? Okay, so our final answer would be r by k. Okay, r by k is 6. From 6, if we subtract the initial 1 or 2, L minus 1, this 2. If we subtract this 2, then we get 4 numbers that are in my range. Okay, so from that, we subtract L minus L plus 1. Okay, so I hope you understand this would be our answer. Okay, so the number of numbers from L to R by K is R by K minus L plus 1. Okay, here you can see our answer was this was 6. So 6 minus L is 3 plus 1, which is 4. So 4 was our answer in this case. Okay. So I hope it is clear to you. We are given R, L, and K. Our final answer would be just R by K minus L plus 1. We derived this formula and we'll just see out this thing, and that's it. We need what we need to do. You can look at the code. Okay, we take the input L, R, and K, and my answer is R by K minus L plus 1. Okay, so this R and K are in int, so this division would be int division, so we'll get the floor value automatically. So R by K minus L plus 1 gives our answer. Now, if this answer becomes, okay, it may happen this answer becomes less than 0, or then we would print just 0 only, because it may happen that, let's say, you are given the range from 3 to 6. Okay, let's say 3, 4, 5, 6 is given to you, your set. Okay, and you are given, let's say k is equal to some 7. Okay, so your r by k would give you 6 by 7. This would be 0 only. So it means 0 is the last number for which we can perform. So obviously, if you subtract that from L, okay, if your r by k is less than L, basically if your r by k is coming less than L, then your L minus r by k minus L plus 1, this would become negative. So if it is negative, you would print 0. That means there is no number in the range. Okay, that thing only I'm handling. If this answer r by k minus L becomes negative, then print a 0. Otherwise, print the answer. Okay, I hope this problem is clear to everyone. Okay, so I think we can move to the next problem now. Okay, so problem B, what we have, that you are given a binary string S of length n. Okay, Iris gives you another binary string R of length n minus 1. Iris is going to play a game with you. During the game, you will perform n minus 1 operations on S in the ith operation. First, you would choose an index k such that this k is in the range from 1 to the length of S minus 1. Okay, and this Sk is not equal to S of k plus 1 if it is impossible to choose such an index, you lose. Then you replace sk plus 1 with ri. Note that this decreases the length of s by 1. If all the n minus 1 operations are performed successfully, you win. Determine whether it is possible for you to win. Okay. Okay. I'll tell you what this statement states. So you are given two strings, R and K. Let's see. Let's take this example. So you are given an integer n and a string of length n and another string R of length n minus 1. Okay, this would be a length 6. This would be of length 5. Then what it is said, you would start with this string s. Okay, you would start with this. These are two binary strings. It would only have 0 or 1 in it. Okay, no other character. So you would start with this string s, and then you would perform these n minus 1 operation for every operation. Okay, if it is the first operation, then you would use this r1, which is 1. Okay, and what you would do, you have to pick up basically any two consecutive indices. Okay, let's say you pick these two indices such that their values are different. Okay, now if you want to pick up these two indexes, this is not valid because both the values are same. So you need to pick up two consecutive indices, I and I plus 1. Okay. So you may pick these two, but their values are same. So you cannot pick. You may pick these two, but their values are same. You cannot pick. These two also same. These two also same. So the only valid way to pick up an index here is this index. Okay. So you can pick this index. Their values are different. 1, 0. So either it would be 1, 0 or it would be 0, 1. These are the only cases. If you pick up the substring that you are picking up, either it would be 1, 0 or it would be 0, 1. Now, so you picked up here. After that, you replace these two values. Okay, these two characters with a single character ri. Okay, so in the first operation, your ri was 1. So you replaced these two with a 1. Okay, so your new string becomes 1, 1, 1, 1. These all are okay. Now these two characters are replaced by a 1. Okay. So this was the first operation. Okay, first operation. Now, then you would move on to the, this is done. Then you would move on to the second operation. Now your Ri is 0. Then again, you need to pick up two consecutive indexes such that their values are unequal. Now you can see for this, if you pick these two, values are same. If you pick these two, values are same. If you pick these two, anything you pick, the values are same. That means you cannot pick up two consecutive indices with different values, 1, 0, 0, 1. Then you would say that you lose the game. Okay, if you cannot pick, then you lose the game. And if you were able to pick, then again you would replace those two consecutive characters with this ri. They would be replaced by 0. That way you would, after n minus 1 operations, this string of length n, every time it get reduced by one length. Okay, here it was of length 1, 2, 3, 4, 5, 6. Okay, here it got reduced to length 5. After the next operation, if it was possible, it would get reduced to 4, then 3. Okay, so after n minus 1 operations, string gets the basically the length of s becomes 1, and that you can understand. Okay, or z, yeah, 1. In every operation, it gets reduced by 1. So from n, it becomes 1. So finally, you would either have a 1 remaining or a 0 remaining. Now, if you can reach this state, then you say that you win the game. And if in between you were not able to perform the operation, then you say that you lose the game. Now, you have to play optimally and select such characters so that you finally win the game. And if it is not possible to win in any way, you would say that you lose the game. So you print a no. Okay. So you have to print yes and no. So for this test case, you can see that we were not able to win. So answer was a no. Okay. Let's look at this next test case. Here our initial string was 0, 1, 0, 0, 1, 0. Okay. Now this is S, this is R. So in the first operation, we have a 1. So we can pick up this, these substring, or we can also pick this substring. This cannot be picked, or we can also pick this substring. This is 0, 1, or we can also pick this. Okay, so we have, actually we have 1, 2, three, four possible options to pick. So we would pick either of them so that finally we are able to win. Okay, we have to select optimally so that we are able to win finally. Okay, so let's say we picked up the first two. Okay, so what would happen if we pick up this? Then this would be replaced by this 1. Okay. So if that happens, this is replaced by a 1. Then this would be 1, 0, 0, 1, 0. This would be our string. This is done. Then again, we have a 1. Okay. Here we can pick this, or this. These are three options. Let's suppose we picked this. Okay. Let's suppose we pick this. This would be replaced by a 1. Okay. So our new string becomes 1, 0, 0, 1, 0. Okay. Then we have this 0. We can pick either this or this or this. Okay. Let's suppose we picked up this. So that would be replaced by a 0. Our string becomes 1 and triple 0. Okay. Then we have a 1. So we can only pick this. So this would be replaced by a 1. So our string becomes 1, 0, 0. Then we have a 0. So we can pick up this and our string becomes 0, 0. Okay, I think 1, 2, 3, 4, 5 operations are they performed, or we did a mistake somewhere. We initially had. Okay, after this replacement, there were only 2 zeros. I wrote 3 zeros here. Okay, so it would be like this: 1, 2, 3, 4, 5, 6, 1, 2, 3. Okay, it was like this. I added an extra 0 here. It would not be present. Okay, so after this replacement, it become 1, 0, 0. After this replacement, it becomes 1, 0, and then it would become a single 0. Okay, I hope this is clear to you. I did an extra 0, but the operations remains the same. Okay, so this way we would finally reach a single digit, which is 0, and we are able to perform all of the n-1 operations. So we can say that yes, we win the game. Okay, so for this test case, our answer was yes. I hope the problem is clear what we need to do. Now, how would we play optimally in order to win? You can look at the constraints. It is n is up till 10 to the power 5. It means we need to find a solution in somewhere order of n time, or n log n at max. So let's look at one observation what is happening here. Okay, whenever we perform an operation, what is happening? Okay, so either we would have Ri equal to 0, or we would have Ri equal to 1. So either we would replace two consecutive characters by a 0, or two consecutive characters by a 1. Okay, let's handle these two cases separately. Now for Ri equal to 0, what is happening? Either a substring of 0, 1 gets replaced by 0, or a substring of 1, 0 gets replaced by a 0. So effectively, if you look what is happening when a 0, 1 gets replaced by a 0, this 1 is getting erased. That is what is happening effectively. This 1 is getting erased. Okay. If you look at this 1, 0 converting into 0, that means this 1 is getting erased. Okay. So in both the cases, you can see that whenever two consecutive characters which are different, they are replaced by 0. That means the character which is 1 that gets erased. The character which is 1 that get erased. That means from this we can conclude that 1 gets erased. Okay. Now what is happening for this case where Ri equal to 1? When Ri is equal to 1, either we would have 0, 1 get replaced by 1, or 1, 0 get replaced by 1. So here you can look what is happening effectively. This 0 is getting erased. What is happening effectively? This 0 is getting erased. Okay. So we can say that for this case, effectively 0 gets erased. Okay. So we can say when Ri is 0, 1 is getting erased. When Ri is 1, 0 is getting erased. That's what is happening effectively in our string S. So we can say if initially in our string S, we have some 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 0, 1. Okay, anything. Let's say we have some random binary string S. Then in every operation, if this Ri is 0, that means one of the 1 gets erased. Okay, so we can decide which of the one will get erased. Okay, now whichever one is towards the border, if it is along with a 0, we can pick up this string and erase this one. Okay, this one is in the border along with a 0, we can pick up this one and erase this one. Now, if you look at this one, this was in the middle of two ones, so we cannot pick this or this and erase this one. So this one cannot be erased, but all the ones that are lying in some border along with a 0, this and this, okay, this, these are these are the ones that may get erased, that we can erase. Okay, we can select one of the one and erase them. That's what would happen if Ri is 0. Okay. What if Ri is 1? Then what would happen? Okay. Again, we have some random binary string in which Ri is equal to 1. It means one of the 0 gets erased. Okay. So in this, if you look, whichever 0 is in the border, okay, the first 0, this cannot get erased. It doesn't have a 1 to the left. So this cannot get erased. But you can see this 0, this can get erased. It is along with a 1. Okay. This 0, if you look, this can get erased. This is alongside a 1. This 0 can get erased. This 0, this 0. All these zeros can get erased. Okay. So what would happen? One by one, we would select any 0 and erase it if Ri is 1. If Ri is 0, we would select any 1 and erase it. Okay. So what would be the most optimal way to erase in order to win? So what is the condition for winning or losing? Basically, what is the condition for losing? When do you lose? If you see, you would lose when you won't have any 0 1 pair or a 1 0 pair present in your string. When would this happen? In what kind of string would you never see a 0 1 and a 1 0? So either my string is going to be all zeros or my string is going to be all ones. This is the only case where if your string becomes a string having only zeros or a string having only ones, then only you can say that you lose. Otherwise, if you have both zeros and ones present, then if you have many zeros, somewhere when this 0 gets transitioned to a 1, we would have a 0 1 pair present. So we can perform an operation. But only when this happens that all are 0 or all are 1, then only we can say that we would lose. Okay. I hope this conclusion is clear to you. So now, if you analyze this problem, you have an initial string. If initially only the string is like all zeros or all ones, then you lose there only. Initially only you can print a no, that you cannot win. Okay, but what if initially you have this string having zeros and ones? Okay, some amount of zeros, some amount of one. Then you would say every time you get Ri equal to 0, your number of ones get reduced. So initially, if you see the count of zeros, with C0, I represent the count of zeros in my initial string. There is 1, 2, 3, 4, 5, 6. Here it was 6. And my count of 1, the number of ones present is 1, 2, 3, 4, 5, 6. It was 6. Okay. So initially, I have this state. I have 6 zeros and 6 ones. In every operation, if Ri is 0, okay, so you have this case. After that, if Ri is 0, it means your C1 is getting reduced. If Ri is 1, it means your C0 is getting reduced. That's what is happening in every operation. I hope this is clear to you. So whenever you get a 0, the count of 1 is getting reduced. Whenever you get a 1, the count of zeros is getting reduced. When do you lose the game? If the count of C1 becomes 0 or the count of C0 becomes 0. If any one of them becomes 0, then you would say that you lose the game. This was our condition of losing. Here, the count of 1, this C1 was 0. Here, the count of 0, C0 was 0. Okay. Basically, so you would lose when either the count of 1 or the count of 0, they get exhausted, they become 0. Okay, that is the condition for losing. So basically what you would say, whatever R you have, you are given some R. Let's say 0, 0, 1, 1, 0, 1, 0. Whatever R you are given, it would have n minus 1 characters, let's suppose. So whenever you get a 0, your C1 get reduced. Whenever you get a 0, C1 get reduced. Whenever you get a 1, C0 get reduced. Until here. Okay. In the last, if after the last operation your C1 or C0 they become 0, that is okay, because you know at the end you get either a 0 or a 1. Okay, so if after the last operation your C1 becomes 0, that is fine, your operations are done. If after the last operation your C0 becomes 0, that is fine, your operations are done. But before the last operation, till here, okay, so till here, if at any point your C0 becomes 0 or C1 becomes 0, then you would say that you lose the game. That's the only condition for losing. So what you would do is uh, till here, okay, excluding this last character, the number of times you have a 0, okay, that many times your C1 get reduced. The number of times you have a 1, that many times your C0 get reduced. Okay, so if so what you would say is in S initially, whatever is there, you get C1 and C0, the count of ones and count of zeros. Okay, and whatever your R is, excluding this, okay, till here, you get some count of, let's say, CR1 and CR0. Okay, the number of ones present in R till here, excluding the last character, and the number of zeros present in R till here, excluding the last character. The last character actually doesn't matter, because before the last character, if you have 0, 1 or 1, 0, then either you have Ri equal to 0, then it becomes 1. If you have Ri equal to 1, like then it becomes 0. Here also it becomes 0 or 1 likewise. So everything is fine if before the last character you have 1 0 and 1 1. Okay, if you have at least 1 0 and at least 1 1 before the last character, then it is fine, otherwise it is not fine. So you would say this, the count of ones in R is CR1, count of zeros is CR0. So I would say that in my S, the count of 1 was initially C1, and for every 0 my count of 1 was getting reduced, so minus CR0 is the remaining count of ones. Okay, this should be greater than 0, and my C0, whatever is the count of 0, minus the number of ones we have in R, that many times my C0 is getting reduced, so minus CR1, this thing should also be greater than 0. If both these conditions are satisfied, we would say a yes, otherwise we would say a no. Okay, I hope this is clear to you. So that's the only condition. Okay, the count of ones in S minus the count of zeros in R, this value should be greater than 0. The count of zeros in S minus the count of ones in R, this value should be greater than 0. And we are excluding the last character of R. Okay, that you have to keep in mind. So if both these conditions are satisfied, then we answer a yes, else we answer a no. I hope this problem is clear to you. Let's look at the code. Okay, what we did, we took the input N, S, and R. After that, what I did is R dot pop back. So I know the last character of R doesn't matter, so I just pop back the last character of R. So this last character gets removed from R. Okay, so I just remove the last character from R. And then I'm just checking C1 is the count of ones in S minus the count of zeros in R. Okay, you can see the count of ones in S minus the count of in R, the count of zeros. Okay, this thing is what I'm telling C1. Okay, here my C1 was the count of ones in S. From that, when we reduce the count of zeros in R, we get this value. This should be greater than 0. Okay, so this C1 should be greater than 0. And C0 is the count of zeros in S minus the count of ones in R. Okay, this C0. If both of them are greater than 0, we answer a yes. Otherwise, we answer a no. I hope this is clear to you. Okay. And if you look at the time complexity, this count function would take an order of n time to calculate the count. So this is order of n, this is order of n. So this whole is taking order of n. This thing is also taking order of n. Overall n and n, this is if else is order of 1. So in overall order of n time, we are calculating this. Space complexity would also be, you can say, an Extra space, or there is no extra space, only the space of string s and r. So extra space is order of 1 only. Okay, I hope this problem is clear to you. We can move on to the next problem now. Okay, let's look at the next problem, which is problem C. So here, what we have is Kevin used to be a participant of Codeforces. Recently, the KDOI team has developed a new online judge called Force Code. Kevin has participated in N contest on Force Code. In the ith contest, his performance rating is AI. Okay, now he has hacked into backend of Force Code and will select an interval L to R, then skip all of the contests in this interval. After that, his rating would be recalculated in the following way. Initially, his rating is x equal to 0 for each I from 1 to n. After the ith contest, if I falls in L to R, this is skipped. Otherwise, rating will be updated according to following rule. If AI is greater than X, his rating increased by 1. If AI is equal to X, rating remains unchanged. If AI is less than X, rating decreases by 1. Okay, that's how the rating is changing. So uh, you need to find out that you have to help Kevin to find his maximum possible rating after the recalculation if he chooses to the interval L to R optimally. Note that Kevin has to skip at least one contest. Okay, so this interval L to R should be of length at least 1. That is also given to us. Now, you need to just find out the maximum possible final rating he can achieve. So I'll tell you what this problem states. Okay, let's take the first test case only first. So basically what we are given is, you are given an array A of length n. Okay, there you need to find out an interval L to R. Okay, so you can just pick up any interval L to R. Let's say you picked up this interval from L to R. Okay, let's say you picked up this interval. Now you need to find the most optimal interval you pick, so that if you pick this interval, what would happen? These three numbers get deleted from this sequence basically, and your new sequence becomes 1, 2, and 6. Now, according to these, okay, these are like the performances in every contest. Okay, so according to this performance, you get a final rating. How is that calculated? You start with x equal to 0. Okay, you go to the first performance. If it is greater than x, if this one, you can see this one was greater than x, which was 0. Okay, then you say you do x plus plus. Okay, your x increases by 1. Basically, your x becomes 1 now. Now, you go to 2. Again, this 2 was greater than x. You do x plus plus. Okay, so your rating increases by 1. X becomes 2. Okay, then you have 6. Again, this 6 is greater than 2. Again, you do x plus plus. So your 2 increases to 3. Okay, this 2 was greater than 1. You did x plus. Okay, so these are the 3 steps that are happening, and your x becomes 3 finally. So with this sequence of operations, your x becomes 3. Okay, and if you had, let's say, instead of 6, if you had 1 here. Okay, so here you had, after 1 you reached 2. If at the end you had a 1, that means this 1 was less than 2, so your x would become minus minus, your rating would drop by 1. Okay, and if this was 2, then 2 equal to 2, your x remains the same, okay, as it is. Okay, that's how this rating change is working. Okay, so here we had 6, let's say it was 6 only. Okay, so finally you get a 3. So if you selected this range, you get 3 as your maximum value. Okay, let's say you select some different range. Let's say you selected this range, only 4 and 5. Then you get 1, 2, 3, and 6. For this, you start with x equal to 0. Here, 1 is greater than 0, you increase your x. 2 is greater than 1, you increase your x. 3 is greater than 2, you increase your x. 6 is greater than 3, you increase your x. So you get x equal to 4 finally. Okay. Now this 4 was greater than 3. So this was a better option to choose this. Okay. What is would be the most optimal here? It would be to choose some LNR here only. Okay. If you choose any single digit, then that would be best, because you can see if you don't remove anything, if you have this, if you don't remove anything, then with you start with x equal to 0, it becomes 1, then it becomes 2, then it becomes 3, 4, 5, 6. So finally you reach 6. Now, since it is given, you need to select at least one value in your range. You need to select at least one contest that is skipped. So just select any one contest, just skip any one contest. Okay. Then that would be the best in this case. Okay. Here you would get, you start with x equal to 0. With 1, it increases to 1. For 2, it increases to 2. For 3, it increases to 3. For 4, it becomes 4. For 6, it becomes 5. Okay. So you finish with 5. That's the maximum you can get if you choose your LNR optimally. So for this test case, your answer was 5. Okay, let's look at a different test case to see actually what is happening. Okay, now in this test case, if you see, okay, you need to select a range of contests that you would skip. You need to select a range L to R so that your final answer is maximized. Okay, so what you would select? So let's say you select this. Okay, here the most optimal was to select all these ones. If you remove all these ones, if you remove them, then you get 1, 2, 3, 4. Okay. For this, if you start with x equal to 0, here it becomes 1, here it becomes 2, here it becomes 3, here it becomes 4. You finish with 4. Okay. So for this, the maximum you can get was 4. You can see your answer was 4. Okay. That was when you select this range. Okay. If you selected some other range, you can see like you have 1, 2, 1, 1, 1, 3, 4. Okay, in this array, let's say you selected this range. Okay, if you selected this range, your array becomes 1, 2, 1, 4. Okay, for this again, if you perform the operation, you start with x equal to 0. Here your x becomes 1. Here your x becomes 2. Here this 1 was less than 2, so your x reduces to 1. For 4, it increases to 2. So you get 2 finally. Okay. Now you can see this 4 was better than 2. So 4 was the maximum you can get for this test case. Now you need to find out how can you optimally solve this problem. Like the constraints, if you see, n is 3 into 10 to the power 5. Okay. One possible way was to just brute force through all the possible LNR. Okay. If you brute force through all the possible LNR, okay, that would be order of n square for the brute force thing. If on the number of possible LNR, that would be if you select any two indices among this n. So that would be nc2, which is n into n minus 1 by 2. So this thing is going to go order of n square if you brute force. And then for checking, if you remove this L to R and then one by one go to every index and calculate, that would again take an order of n extra. So overall order of n cube was the brute force approach, but you can see with the given constraint, an order of n cube won't be accepted. So you need to find some optimal way to solve this problem in some order of n or order of n log n at max. Okay, these are the expected time complexities in which you need to solve this problem. So let's think how can we solve. Okay, so like during the contest, I thought of many greedy approaches that maybe we can like we can keep on increasing and remove some gaps in the middle. But again, there would be some increasing, decreasing array. In that, what you remove, okay, that you cannot like directly like guess that. Okay, so one approach was just fix some L. Okay, so one by one, just fix your L and then try to calculate. Okay, okay, if we think like that, let's say we fix our L, then till here, definitely we are, all the values are coming. So after performing the operation, still here, you would get an X. Okay, so if you fix your L, then till here, you got, after all these operations are performed, you got an X. Now for that X, what is the most optimal R you choose, so that after that, if you take, then you get the best possible answer. Okay, you that was again taking an order of n time to calculate the most optimal R. In some, if you want to try for a fixed L, what's the most optimal R, then that also depends on the x that you get. Okay, so you cannot pre-calculate that before, because for different L you get a different x. Okay, so that was the problem coming there. Okay, so then what the approach I thought was like a DP approach, that if you look at the array, okay, if you look at your array, you have some array, you would pick up some L and some R. Okay, let's say you picked up this L and this R. It means your array is, if you look, effectively divided into three parts. This is the part, okay, which you are selecting. This is the part which gets ignored. And again, this is the part which is present. Okay, so basically whatever L and R you select, you are dividing your array in three parts. Okay, so one of the range from L to R, it gets removed, and then till here you perform the operations. After that, it continues from here. Okay, so basically for every index, if you look, like what are the cases? Either any index would lie on this part, or the index would lie in this part, it is removed, or it lies in this part. Okay, these are the, like, you can see the three possible cases for any index. Now, uh, let's assume, like, I was trying a DP approach. So in DP, generally what we do is we take DPI as, what you need to compute is for the whole array, what is my answer? Basically for the whole array, what's the most optimal L and R? What's the most optimal range that you remove from the array, so that finally you get the maximum X? That's my answer. So if you want to calculate for the whole array and you somehow calculate for some sub part, then can you recalculate for the other subpart? Okay, if you can find that, then you can try a DP approach. Okay, so let's assume that we want to find our answer for this whole array, and we have already found our answer if this was our question, till n minus 1. Okay, like till I minus 1, if you have found, then can you calculate if this extra element is added to the array, what can be my final answer? Okay, so if we would try to write the transition for that. So basically what is the state I'm taking is DPI just represents my answer for, if I take the subarray from this. Okay, basically my DPI represents that if in my array in my array A, if I only have up till index I, okay, rest elements are not present. If that was my question, okay, if my question, in my question, if I was only given up till index I, okay, if only that much array was given to us, then what is my answer? That's what DPI represents. Okay, so I can say my final answer, that would be DP of n, or n minus 1, like in one based. Okay, I'm taking one based only. So from 1 to I. Okay, so my final answer would be DP of n. Basically, that DP n represents the subarray from 1 to n, is basically the whole array A. So if the question was the whole array A, which is the question, then my answer is DPN. Okay, and my DPI is, if the question was up till index I only, then what's my answer? Okay, so answer for this subarray from 1 to I, that's my state. Okay, and this is my DP state. Now, how can I write my transition? Okay, let's see. I have an array A. Let's say this is my index I. Okay, this would be my index I minus 1. This is my ith index. This is my I minus 1th index for the array A. Okay, if I want to calculate my DPI is my answer if only this array was given as a question. Okay, and I assume that I have already calculated till DPI minus 1. So how can I write DPI in terms of DPI minus 1? So if till I minus 1, I selected some range and found some optimal answer. Okay, what is the maximum final X that I get? So for I, there can be two cases. Either the selected range for this is somewhere before I, If it was somewhere before I, that would be covered in my I minus 1. Okay. So either I take the best possible answer till I minus 1, where a range L to R is already selected. So dp I minus 1 is the best possible answer till I minus 1, where some range L to R is already selected. To that, when you add this index, so you would just check if this value, if this AI, okay, if this AI is greater than, okay, the X I take is dpi minus 1. So if AI is greater than dpi minus 1, I do a plus 1. Okay, if it is less, I do a minus 1. If it is equal, I do a plus 0. Okay, so like let's represent this value. Either I would do a plus 1 slash minus 1 slash 0. Okay, that's what I would add it. Okay, depending on, like, we have three cases depending on whether AI is greater than this, less than this, or equal to this. I add either a plus 1, minus 1, or 0. Okay, so this would be one case where I assume that my L to R range is before I only. This I is not included in my L to R range. Then this would be definitely considered till I minus 1. So whatever is the best possible answer till I minus 1, take that. To that, add this, the contribution of the ith index, either plus 1, minus 1, or 0. Okay, so this is one case. So either this would be one of the answer, or when would this not be an answer? When this I is also included in the range. Okay, that means we have a range ending at I. Okay, so till here, either it would be some range ending before I, okay, or the range is ending at I. So only for the case where my range is, my L to R range is ending till here, till I. So for that case, what's my best answer? For that case, now I know my R is here. My R is at I. Then what's the best L I can choose? The best L I can choose is, okay, if I choose this as an L, that means in my answer, I would have till here whatever. If I perform the operations till here, what's the answer? Okay. If I choose L as this, then if I perform operations till here, what's the answer? If I choose L as this, then if I perform an operation till here, what's the answer? So basically, for all possible, for this prefix, for this prefix, for this prefix, for all the prefix up till I minus 1, if you calculate the answer, then the maximum among those would be the best answer. So if you calculate a prefix array where you have stored that for this prefix, if all the values are considered, okay, that you can easily calculate that no value is removed till here. Okay, so if no value is removed till here, then what's the best answer? Okay, then to that you take the prefix max with this, prefix max with this. Okay, so for all the L from 0 till here, whatever is the maximum, whatever is the maximum value for this, okay, for all the prefixes till here, whatever is the maximum value, that you would take. Okay, so take that value. If this was the maximum, take that value and just consider all the values ahead of this as removed. So your final DP state would be that maximum only. So either if you are removing before that, then this is your state. This is the case one when your range is before, and when your R is at this I. For this another case, when your R is at this I, you take the prefix maximum. Okay, so like prefix maximum, you would pre-compute this prefix maximum of I minus 1. Okay, you need to remove at least one value. Okay, so this, if you are removing this value, then you take the prefix maximum till here. You won't take the prefix till here, because then you're not removing any value. And you know you need to remove at least one value. So you take the prefix till here. So prefix max till I minus 1, or this thing. So the maximum among these would be your DP state. So I hope this transition is clear to you. This you can say is your DP transition. Okay, so if this transition is clear, this base case is, this state is clear, then only thing remaining is the base case. So the base case would be, you can say that like DP0, DP0 represents that for the empty subarray. Okay, or for the, like let's take DP1 only. DP1 is when you have only one element. Okay, so if there is only one element, then definitely at least one element need to be removed. So it would be removed with zero element, your x would remain zero. So dp1 is equal to 0. This you can say is your base case. Okay, after dp2 that can be computed using. So from I equal to 2, that can be like from I equal to 2, all the remaining states can be computed using this. For I equal to 1, you say that if you have only the one value, then you would definitely remove that. So you can reach 0 only with no elements. So this is your base case. This is your base case. This is your DP transition. And this was the state of your DP. So I hope this is clear. So you can now very easily write the code when you know the base and transition. The final answer that you print would be DPN. Whatever is the value of DPN, that would be your final answer. So if this is clear to you, I think we can move to the code now. Okay, so what I'm doing here is I take the input. Okay, this input part is done. And then first I would compute this prefix maximum. Okay, so for computing the prefix maximum, okay, this, as I told, this I have to pre-compute this prefix maximum. So what I would do is I would start whatever array A is given to me. Okay, let's say it's 1, 4, 1, 2, 5, whatever is there. So what would be my prefix maximum? So for the first index 1, for index 1, we would just start computing my current value. Okay, so I start with x equal to 0. Then if I get a 1, I do an x plus plus. So my x becomes 1. Okay, so prefix max for the first index, it would be 1 only. So till here, if we have only 1, our answer would be 1. Okay, now for the second index, we have got a 4. We do a plus plus, it becomes 2. So here we have a value 2. I'll compare it with, because I'm taking the prefix max. So either the current value is 2. So either it would be 2 or 1, whichever is maximum. So here among 2 and 1, 2 was maximum. So I take 2. Okay. So for 1, what we have is for uh, 2, 1 is less than 2. So this 2 gets reduced to 1. So my current value is 1 here. Okay. So my current value is 1 here, but prefix maximum would be maximum among these, which was 2. So this value becomes 2 actually in the prefix array, prefix maximum array. Okay. So the current value here was 2, but in the prefix, the maximum value, when I take max with prefix I minus 1, it becomes 2. Here now current value is x, and this 2 is greater than 1, it increases to 2. So the current value is 2 here, and the maximum before that is also 2. So it would be 2. Now we got a 5. So this x get increased to 3. So the current value is 3 here, and which is the maximum before that. So this would be my prefix maximum array, which I'm going to use. Okay. So I hope how I'm computing it is clear. So in the code, how I would compute it, I start with x equal to 0 for every index. Okay, I have taken this array as one based index from 1 to n. Okay, keep that in mind. So for every index from 1 till n, if ai is greater than x, I do x plus plus. If it is less, I do x minus minus. Otherwise, no change to x. Okay, and then I take the prefix I as the maximum among prefix I minus 1 or the current value of x. Okay, so this way I compute my prefix maximum. Okay, then what I do is I calculate my DP. Okay, so I take DP of n plus 1, 0. My base case is DP1 is 0. This was my base case. So I write the base case, DP1 is 0. Okay. Then I move to my transitions. So I run a loop from I equal to 2 to n. I want to compute my DP. Okay. So now what was my transition? My transition was either it is prefix max of I minus 1 or dpi minus 1 plus this. So this would depend on whether ai is greater than this, less than this, or not. So I compute this thing. I take x is equal to this. So if this is taken as an x, then I depending on the value of ai, I do plus 1, minus 1, or plus 0. So like here I'm taking y as dpi minus 1. If AI is greater than y, I do y plus plus. If it is less, I do y minus minus. This way I computed the y taking dpi minus 1 as the initial y and then performing the operation for AI. Okay. So either my dpi would be this y. So this y is actually this thing, this plus 1 minus 1 or 0. Okay. So this thing is my y, or the prefix max till I minus 1. The prefix max till I minus 1. So this way I compute my dp state. So this transition is done. After that, my final answer is dpn. As I told, my final answer would be dp of n. So I print my final answer. I hope this code is also clear to you. Okay. Now, if you look at the time complexity, this input part is taking order of n. Now this prefix computation is an order of n. And then this dp is of size n. So here for I run a loop from 2 to n. This is order of 1, order of 1, order of 1. So all these are order of 1 operation, constant time, which is done n times. So order of n overall. So an order of n loop here, order of n loop here. Overall time complexity is order of n. Okay. And what would be my space complexity? I'm using a dp vector of size n. That's the extra space I'm using. So it would be order of n. Okay. I hope this problem is completely clear to you. If there is any doubt, you can ask. Okay, fine. So I think we can move to the next problem now. Okay, so problem D, which is you are given an undirected graph with n vertices and m edges. Okay, you can perform the following operation at max 2 into max of n comma m times. Okay, so what is the operation? Choose three distinct vertices A, B, and C. Then each of the edges AB, BC, and CA do the following. If the edge exists, if the edge does not exist, add it. If it exists, then remove it. A graph is called cool if and only if one of the following condition holds. The graph has no edges or the graph is a tree. Okay, so if the graph has no edges or if the graph is a tree, then the graph is called cool. So you have to make the graph cool by performing the above operations. Note that you can use at most 2 into max of n comma n m operations. It can be shown that there always exists at least one solution. Okay. So basically what is given here is you are given some graph. Okay. In that graph, you need to perform some operations. Okay. The graph has n vertices and m edges. Okay. So here you can see this graph has 6 vertices and it has like 1, 2, 3, 4, 5, 6 edges also. Okay. So graph is given in this form. This was the fourth test case. So n is 6. M is 6, so 6 edges and 6 vertices, and all this information for all the edges is given here. So that way we constructed this graph. Now for this graph, you need to find some way in maximum of n comma m times. Okay, so you can use at max. Okay, so max 2 into max of n comma m. For this case, it was 2 into 6, which is 12. So 12 is the maximum number of operations you can use, and in that many operations, you need to basically convert this graph into, you have to make this graph cool. Okay. So cool is either you have to make it a tree or you have to have a graph with no edges. Okay. That is the definition for cool. Okay. So how it is done here in the first operation. So in each operation, what you can do is you need to select 3 vertices. Okay. Let's say you selected these 3 vertices here. Now, you can see in the initial graph, this was an edge, this was an edge, this was not an edge. Okay, so this edge was not present in my initial graph. So after selecting these 3 vertices, okay, for each pair of vertices, okay, if you look at this, an edge was not there. So now you would add an edge here. Okay. Now here you can see an edge was there. So you would remove that edge. Okay. So this edge gets removed. Here you can see an edge was there, so you would remove that edge. You can see this edge gets removed. Okay, so this was the operation when you selected these three indices. Okay, so when you selected this as ABC, then this graph having these two edges got converted to this graph having this edge and not these two edges. Okay, so this was one operation. Like here you can see after this operation only, this graph, if you see, this is a tree. So it was already made cool by one operation only, but you can perform more operations also. Finally it should become cool. Okay, so if it, then also it would be a valid answer. If you are perform, you don't need to minimize the number of operations. Basically you can use 2 into max of n comma n operations, so you cannot use more than that. Okay, but if you are using less than that operation, you can use any number of operation. Even if it has become 3, you again, by performing the next operation, you made it as a not tree, so it is no more cool because it has a cycle. Then after one more operation, it again became a tree. Okay, so finally, if it is a tree after a sequence of operations and the number of operations are not more than 2 into max of n into m, then this is a valid answer. Okay, so you have to just find such a way. Okay, so this was one way for this particular graph. After these three operations, it finally became a tree, so it is cool. So this was okay. Okay, so how can you solve this problem? So what you have is, you are given some graph. Okay, so if you are said that a graph, an undirected graph, okay, so this graph can be of any form. Okay, it may have many components also. Okay, something like that. You have some random graph given to you. Now you need to convert this random graph either into a tree or a graph having no edges. Okay, so either remove all the edges from the graph if it's possible, or convert this graph into tree. Okay, so what is the definition for a tree? A tree is basically a graph having, okay, so what is a tree? If you don't know, is a graph. Okay, it is a connected graph. Okay, so basically a graph which is, the first thing is, it is connected, it has a single component, and the second thing is it has no cycles. Okay, these are the conditions for a graph to be a tree. Okay, I hope you know that. So we need to make sure these two things. First is, make this whole graph connected, a single component. It should not have more than one component. Here you can see these, there are 3 components in the graph. And the second part is, it should not have any cycles. Like here you can see this is a cycle, this is a cycle, this is a cycle. So you need to remove these cycles. So how can you do that? Using the operations given to you. Okay, so what is the operation given to you? It is given that you select any 3 edges. Let's say you select these 3 edges. Okay, what would happen if you are selecting these 3 edges? So if you are selecting these 3 edges, then you would look at this, like these 3 nodes. You would select 3 nodes, not 3 edges. So if you are selecting these 3 nodes, you would look at each pair of edge that is existing among these nodes. So this edge, so this is existing, so remove it. This edge, this is as existing, remove it. Now this edge is not existing, so add it. So if you are selecting these 3 nodes, okay. So if these 3 nodes are selected, then what would happen? These 2 edges would get removed and an edge would get added. Okay. So this edge and this edge gets removed and this edge gets added. That is what would happen if you select these 2 nodes and do an operation. Okay. Like if you can select these 3 nodes and do an operation, what would happen? These 2 would get removed and this would get added. Okay, so maybe like you can see after this operation, this cycle that was existing here that got removed. So by some operations, the cycles are getting removed, but also here you can see after the operation, it one more extra component also came here. Okay, so this node got separated from this component. Okay, so by operations, you can separate it into two components, remove cycle, or maybe if you look at these three edges, if you select these three edges, what would happen? This gets removed and these two gets added. So here you can see that these two were different components. Now they are in the same component. Okay, so these two components got connected. That also you can do. Okay, now you need to connect these two components. So what you can do? Maybe you can select these three nodes. Now they don't have any edge, so all the three edges get added. So this again got connected to it, but it also created a cycle. Okay, so you'll have to remove the cycle also. So what is the most optimal way to connect all the components and also remove all the cycles? That also we need to make sure it should be connected and no cycles. Or one more thing you can do, either it make it a tree, or what you can do is make it a graph having no edges. So what is a graph having no edges? It means it would only have nodes. Just remove all the edges from the graph. Okay. So if a graph having n nodes gets separated into n different components, that's what is a graph with no edges. So if all the nodes get separated into different components, that means it doesn't have any edge. That is also a cool graph. So this is also cool. So you can make either of the two things. Okay, so these was some observations and all that initially by looking at the question that we noted. Now let's see how can we solve this problem. What is the way to solve this problem? Okay, so after a lot of thinking, I got to an approach that what we can do is, the first thing is, okay, like making a tree was a little complicated. You can see that you have to make them connected. Okay, so you were able to make it connected. But removing these cycles was a bit tricky part. Like if you try, like if you have some cycle, okay, how can you remove this cycle using the given operations? How can this cycle be removed? So like if you take these three nodes, what would happen? These two get erased and this get added. So your cycle was reduced from a size of 5 to a size of 4, but this extra node came in the picture. Again, you can select these three nodes. Okay, so these two get erased, this get added. So your cycle got reduced in size, but this node got separated. Now, if you have a cycle of size 3, then you would select all the three nodes and all the three edges, basically all the three edges, they get removed. So what happened is all the edges got removed from this cycle basically. So while trying to remove the cycle, what I observed that I can actually make it a graph with no edges. So then I started to try to, instead of achieving a tree, started to try to achieve this thing, a graph having, basically a graph having no edges. Okay, let's say we are trying to achieve this. Okay, but again, it was a little complicated. For cycle, you can see we were able to achieve, but if you have some random graph, there is some cycle, but there are some other nodes also. Okay, in that, like, again, it was a little tricky. So I tried to do some approach that, let's start with a single node. Okay, let's consider one node. What I want to achieve is I want to remove all its edges. Okay, so it would be of some form. This is one of the node which is connected to some other nodes. Okay, it would have in its adjacency list, let's see, these are the nodes connected to it. These are the edges it is connected to. Okay, and here again, this would have something. Okay, some network, maybe they may be connected to each other also. Okay, so here some graph would be there. Okay, so if we start with this node, we are trying to remove all the edges connected to this node. What we can do, we can pick up these three nodes. Okay, just pick any two of the child nodes. Okay, so what I'm telling, that for these node, these four are the children of this node. Okay, so select any pair of children, select these three nodes. What you do, perform an operation here. So these two edges get removed and this gets connected. Okay, so no problem. We removed two edges from this node. Okay, now how to remove other two edges? Select these nodes. So basically perform an operation with these three nodes. These two get removed, this gets added. Okay. Now this node got separated, it has no edge now. Okay. But what if instead of this, like here it has four nodes which were its children. Let's say it had only three nodes that were its children. Okay. Again, here these nodes have something there. Okay. Some graph is there. I'm only considering this node. Okay. So for this node, if I pick pair of children, I'm able to remove these two. Okay. Let's say I perform the first operation, these two got removed. But after that, when it has only one edge remaining, then I cannot remove this edge like directly. When it has two edges, then selecting both the nodes A, B, C, these two got removed. But when it has only one edge, then what is the C that we are going to? This would be A, this would be B. What is the third node through which we would remove? Let's say there is some node connected to it which we are taking it as third node. Okay. So let's say there is some third node which we are taking. Then if we are removing this and this, then this is getting connected. So by removing this edge, but one more edge got connected. So basically for this node, we cannot remove this edge. So here in this case, when a node has three children, then I cannot completely separate that node. So what I can do is I can try to make it a tree now. This node, if it has odd number of children, I remove all pair of children that I can remove. Then it would be left with one, basically one child. Okay. So it's connected to that. So let's say we leave that and we move to this. Okay. Now in a tree, we would have a single component from this parent. We would move to this child. Now for this, we would again check for its children. Okay. Now this node would have some children. Okay. So that what I'm representing. So this node would have some children. Okay. Let's say this node has even number of children. Then taking a pair of children, I would be able to remove all of them. And if this node also has odd number of children, okay, if this node also has odd number of children, then we can perform an operation and remove all the pairs of children. Okay. So if these two nodes get removed, this get added. Okay. So I can remove these two children, but one would be still left. Okay. So what I did, remove all the pairs of children that I can remove. Then one child would be still left. Okay. So move ahead. Okay. This you can see is a connected component. Okay. This is not there. So from here, I remove these two pairs. Then I move to here. Then I remove these two pairs. Then I moved here. Okay. Again, for this, I would check. Let's say it has even number of children. Okay. Then what would happen? These two children, by using one operation, these two children gets removed. Okay. And this gets added. So when we get a node for which it has even number of children, then all those children would be removed, all the edges would be removed. So then we would stop there. So this gets separated. So this becomes a component. Okay. And what kind of component it would be? It would be a linear. You can see that every time we were left with one edge, then we moved ahead. We were left with one edge, we moved ahead. So this would be a linear, you can say a lean component having linear edges. Okay. No node has more than one edge. If it has more than one edge, we remove it. Okay. So and if it has even number of edge, all the edges get removed. So it gets broken down into like this. Okay. So basically by performing this, the whole graph would get broken down into something like this. One component here, some component here, some separate here, some separate components here. Okay. So you can see by performing these operations, and how many times are we performing? Whenever we are removing a pair of edges, if initially there were m edges, then two edges get removed, one edge get added. So -2 + 1, basically a -1 on edges is done. So if there are m edges, then at max we would have m operations of this type. After m operations, all the edges would get removed. So by converting this graph, some random graph. By using this type of operations, I converted this random graph into graphs having these linear components only. And this would take maximum of m operations. Okay. In maximum of m operations, I am able to convert this graph into a graph having these uh, all the components, all the linear components only. After that, what we need to do is, if okay, there would be two cases. Either it would be like this, where some components are more than one, or it would be like this, where all the components are like single node only. So this would be a graph having no edges. So here only we would just print out whatever answer that we got. This would be a valid, this would become cool already. Okay, this has already become cool because it has no edge. Or it would be a case like this, where some of the components have some linear component. Some components are a single node and some are linear. So if we have something like this, we need to convert it into a tree. So in order to convert into a tree, we need to connect these components together. That's what we need to do. So how are we going to connect these components? Okay, if you take any two of the linear component, what we can do? Take let's take this node and this node and perform an operation. Okay, so the last two nodes from one of the component and the starting node of other component, if we take these nodes, what would happen? Okay, the last two nodes of one and starting of another. Okay, this node gets removed, this get added and this get added. Okay, so this and this gets added and this gets removed. That's what would happen. Now you can see this becomes another component, which would be a tree. It would not have a cycle. Okay, you can see this is a was a linear component. This was a linear component. What happened? In between this came this component. Okay, so you can see this is a tree. It would not have a cycle. Again, now we got a component of a tree. Then just connect all the components one by one. Okay, next we have this component. Okay, this has a starting edge. Now just take any one component of that. Okay, what is happening? Where whatever component you take, this edge gets removed and this get added in the middle. Okay, this whole component gets added in the middle after this edge gets removed. Okay, so that's what you would do. This edge gets removed and this component gets added. So this component also got merged with it. Now let's merge this component. Okay, so you have this edge, take any edge in that tree. Okay, merge this, remove this. Okay, so perform an operation with the starting node of this tree, of this linear component. So what we would do, perform an operation with starting node of this linear component and remove this. Okay. Okay, so it became like this. Now one component is left. Again, take the starting node of this linear component, take any edge, connect it, remove this edge. This also gets added. Okay. So what we did, removed this edge, connected this. Okay. So this finally became a tree. Okay. I hope how I'm making it is clear. So the first step that I did is, from the random graph, I started with a node. So I would apply DFS basically, go to every node until it is visited. And if it has more than one edge, then just take a pair of edge, remove it. Take a pair of edge, remove it. Okay, perform an operation and remove it. At last, either if it had odd number of children, then it would be left with one child, or if it had even number of children, then it would be left with no child. If it is left with one child, then move further. Okay, move further in your recursion, that let this be a component, move here with this as parent, look at all its children. If it has even number of children, remove all. If it has odd number of children, remove all except one. So one by one do it. Whenever it has even number of children, this loop gets broken and this became a component. Okay, so what I would do, whenever it has no children left, that is, it has even number of children and all of them got removed, so this is the end of a component. So we would store the end of a component in some structure. Let's say in some set we store all the ends of the linear components that we have. Okay, so finally this graph got broken down into some linear components. Okay, now when it is broken down into some linear components, if all the component size is 1, then it is a graph with no edges. So it is already cool. Print your answer. If it has at least one component which has more than one edge, then we would start with that component. Okay, and start to form our tree. So what we would do, we would take that component, the last two nodes, and the ending point of every component. Okay, perform an operation with that. Ending point of next component, perform an operation with that. Ending point of next component, perform an operation with that. Likewise, we would just connect all the components with one operation, and that way this would be connected. So this conversion would take m operation at max, and here we would have at max n components. There are n nodes. So n operations at max here. So maximum number of in step 1, we took at max m operations, and in step 2, converting from a number of linear components into a tree, took at max we would have n components, so n operations at max. So in total we would have at maximum m plus n operations, so which is obviously less than equal to 2 into max of m comma n, which was the maximum limit given on the number of operations we can perform. So max of m, if m is greater, it would be 2m. If n is greater, it would be 2n. So n plus m would definitely be less than the 2 times greater value. If m is greater, then n plus m would be less than 2m. If n is greater, then n plus m would be less than 2n. So I hope with this process in m plus n operations maximum, we are able to convert this graph into either a graph with no edges or a tree. Okay, so we are able to make this graph cool. I hope the approach is clear. So we'll look at the code now. How are we implementing this? Okay, so let's move to the code. So what I'm doing here, first thing, I took the input n and m, n edges and n nodes and m edges. Okay, then to store a graph, we need an adjacency list. So I initialize this adjacency list. Now, one more thing. What I'm doing in every step, what I'm doing is there were some 3 nodes. In every operation, what I'm doing, I'm removing some edge or adding some edge. So in between, I need to remove some edge and add some edge. So if you are taking a normal adjacency list, which is a vector of vector, so if you normally what we do, how we take an adjacency list is you make and like if you have n nodes, then for m you have a list of nodes connected to it. For 2 you have a list of nodes connected to it. Okay, that up till n you have a list of nodes connected to it. Now if you are storing like this, then whenever you are changing it, let's say there was 2 3 and 5, let's say these were the 3 nodes. This 2 and 5 were having an edge, 2 and 3 were having an edge, 3 and 5 were not having an edge. If you perform an operation on this, then after the operation, this 2 and 5 edge gets removed. Then how would you update your adjacency list? In 2, you would find this 5 and remove it. And in 5, you would find the 2 and remove it. Okay, so if you are storing a normal adjacency list, then erasing from a if this is a vector or an array, then erasing in a vector would take order of n time. So this won't be optimal if you are erasing it like that. So you are traversing, and in every operation, if you are erasing in order of n time, overall complexity would go n into whatever the number of operations is, n plus m. It would go the n square or m square. Okay, and you can see this, the constraints, n is up to 10 to the power 5, m is also up to 10 to the power 5. So with these constraints, n square or m square won't be accepted. So you need to do it optimally. So what I would do, instead of storing this vector, okay, so if for erasing, we would have to erase. And when this node gets added, then addition you can easily do. In 3, you would do a pushback 5. Okay, you do a pushback 5, and in 5, you do a pushback 3. Addition would be done in order of 1, but this erase thing would take order of n if you're storing a vector. So what I would do is, instead of using this instead of storing this as a vector of vector, I would store this as a vector of set. Okay. So this would be a set instead of vector. In set, the erase would take order of log n time, and addition would also take, insertion would also take log n time. So my overall complexity in overall complexity, a log n extra would only be added. So that would be fine. So what I would do is I would take my adjacency list as an array of set. Okay. So here, instead of for one, I would to store the set of indices, set of nodes which are adjacent to one. Okay. Set of nodes adjacent to two. Okay. So adjacency, array of a set would be my adjacency list. Okay. And this is up till 1e5. Okay. So at max, I had 1e5 nodes. Okay. And was up till 1e5. So I initialized it with 1e5. Okay. Now, after taking the input, what I'm doing, I'm just clearing this adjacency I. So all the sets up till n from 1 to n, they got cleared, because in the previous test cases, I'm declaring this adjacency as a global variable, so that I can use in my DFS functions and all. That's why I declared it global. Otherwise, I can declare it inside here only and pass it by reference in my DFS function. That would also be fine. Okay, I have declared it global. So in my previous test cases, this adjacency I may be filled up. So I would first clear it. So I would run a loop from 1 till n and clear all the adjacency I. Then for every edge, okay, I take the input u and v. So there is an edge from u to v. So in adjacency u, I insert v. In adjacency v, I insert u. Okay, so that way I am updating my adjacency list. Okay, so once I have formed my graph, okay, I have added all the edges. My graph is formed. Then initially only I would check if already there are no edges, m is 0. That means there is no edges in my graph already. Then I don't need any operation. It is already cool. So I print 0 and return. Okay. No operations are needed. Now, if I don't have this case, okay, then I would compute. So I have this visited vector that I would assign with 0 initially. So this is also declared global vector of int visited. Okay. So this so I'm running a DFS for every node. I'm traversing through every node. So in my step 1, where I'm converting that node into linear components. So I take a visited vector. In this answer array, I would just store all my, whenever I perform an operation, I would add that to my answer vector. Okay, so this answer is a vector of vector. Okay, so this is a vector of vector answer. So inside my answer array, I would add the 3 nodes A, B, C that I have to print. Finally, I have to print it, like you can see in my output. I have to print if the answer has 3 operations, then for every operation I print ABC, ABC, ABC. So my answer is a vector in which I would store all the ABC whenever I perform an operation. And this set would store, okay, I have a set ST that would store basically all the ending points of every component. So this set stores end points of every component. Okay, as I told, whenever I have some components here, so for all the components, there would be some ending point. So through those ending point only, finally we would connect. So while forming the components only, I'm storing the ending points in a set. Okay, so these three initial things, they are cleared before adding anything. So now I would perform my DFS. So I'll go to every node. If it is not visited, I perform DFS I with parent as -1. Okay, now let's look at my DFS function, what I do inside. So I'm running a DFS on X with, okay, when I'm running a DFS on a node for which parent is -1, that means it doesn't have a parent. It's an initial node. Okay. So then I would take parent as -1, which was represent it doesn't have a parent. Okay. Now I'm running a DFS on X. I mark visited X as 1. Now I make a vector of child int which of child. Okay, so I store all the childs of that node. So I go to adjacency of X. If I is equal to P, if it is one of the parent, I do continue. And for all the remaining edges, all the remaining nodes in my adjacency list, they are the childs. So I push back them in my child vector. Okay. So in my child vector, I have stored all the childs of x. Okay. So all the childs of x are stored in the child vector. Now, if the child vector, the size of this is greater than equal to 0, now till the time this child vector has size more than 2, we would remove 2 of the nodes from that. So basically, we take the last value in my child vector and the last second value. Okay. Child dot size -2 gives me the last second value. Child dot back gives me the last value. So my operation would be performed with the last second value, and my A would be X. Okay. So how I'm performing the operation is whenever I have a node for which, let's say, I have 4 children. Okay. So this is child number 1, 2, 3, 4. Okay. So in my child array, I have 1, 2, 3, 4. These are the 4 children. So first I would remove the last 2 children. Okay. Every pair of children, one by one, I would remove. And then if it is odd, one child would be left. If it is even, all of them would be removed. So I take the last 2, so 3 and 4, and this is X. Okay. So I perform the operation between X, 3 and 4. So the last 2 values and X. So we'll perform an operation with the last 2 values as B and C and X. So answer dot puts back X, B and C. Okay. So, and from my child vector, I would pop that back these 2 values. So these 2 values get removed from my child vector. It would get reduced to this. Okay. So now, in my answer, I would put back X, B, and C. Now I also have to perform the operations. So I have to remove these 2 edges and add this edge. So when we remove this edge in the adjacency list of X, I would erase 3, and from 3, I would erase X. So from X, I erase B, and from B, I erase X. So the node between B and X is removed. From X, I erase C. From C, I erase X. So the node between X and C is removed. Okay, so this is B, this is C. So from X, I erase B. From B, I erase X. From X, I erase C. From C, I erase X. So after all these 4 erase operations, these 2 nodes gets erased. Now I have to add this edge. So either I would add this edge, or if this edge is already there, then I would remove this edge. So I would check whether this edge exists. So in my adjacency list of 3, if 4 exists, okay. So if in adjacency of B dot find C is equal to B dot end, it means in my list B, I did not find a C, then it would be equal to end. So if I did not find a C, then I would add this edge BC. So if I have to add the edge BC, in B I insert C, in C I insert B. And if not, if it is already present, then I would erase the edge BC. So if from B I erase C, from C I erase B. Okay. So that way my operation is performed from X, B, C. Okay. So X to B and X to C, these 2 edges get erased, and we check whether there is from B to C. If it doesn't exist, we add. If it exists, we erase. Okay. So these nodes are updated. My operation is performed. Okay. So we do this until the size of my child vector is greater than 2. Okay. So after the first operation, this get reduced. It's still 2. Then again, we take these 2 values and perform an operation. After these 2 removals, my child vector becomes empty. So either it would become empty or it would have some one value remaining in that. Okay. So then I would check if the size of my child vector is 1, it means there is one edge still remaining. Then we would perform DFS and go to that edge. Okay. So we would just try to form our component. We would go to the next edge in my component. Okay. If the size of child is 1. So we perform DFS. Child 0 is the only value present in my child vector, and X is the parent. Else, if the child vector is finished, that means all the children are removed, then I would say that this X was the last node in my component. Now I would have a new component. This component is over. So I insert this X into my set. Okay. So if this in my set ST, what I'm storing is the last nodes of every linear component. So since after that, I'm not moving ahead. So I insert X into my set. So this was the last node of my component. It get inserted. Okay. If it was not the last node, we perform a DFS and move ahead. Okay. So this way, I hope this is how we perform the DFS, and this way I do the step one, which is converting this graph. Okay. So step one is done here. Okay. I go to every node. If it is not visited, I perform a DFS. So after this, step one is done. So this graph is converted into a graph having only linear components. Okay. So graph is converted to a graph having only linear components. Now I have to make this, convert this graph into a tree. Now I have to perform the step two where I would convert these linear components into a tree. So I have some linear components. Okay. Now I have to add these components. And I know the last nodes of every linear component is stored in my set ST. Okay. So these last nodes, they are stored in my set ST. Okay. So the last nodes of every component is stored in my set ST. Now I have to start with a component having more than one uh, size. Okay. More than one node. Okay. If I start with this component, then I don't have one more node through which I would join the other component. So I have to start with at least a component having more than one node. If all the components have a single node, that means it is already cool. I have no edges. So first from my set ST, I would find which ending point has in its adjacency list at least one more node adjacent to that. That means it would have more than one node in its component. Like if it is a single node in that component, it won't have any edge. And if it is not a single node, it would have a edge. So what I do is I go to every value in my set. So I is all the ending points of my component. If adjacency I dot size, if it has any size, if it is not zero, that means that node is of size more than one. That component is of size more than one. Then I would take A is equal to I. I found the first component that I found, which is of size more than one, we would start with that component. Okay, we would start with that component and start adding all the remaining components to it. Okay, so I break out, I set A is equal to I. Okay, I erase that component from my set. Okay, erase that I, so that when I add, okay, so while adding, what I would do from this component, all the remaining components one by one I would add. So this is already added, so I remove that from my set. Okay, I erase that from my set. Now then I would go to every node in my every value in my set and add that component to my node. Okay, so I break out. So in A, I got the first component, the ending point of the first component, which is of size more than one. And if A was initialized with -1, if there was no node having more than one size, then A would remain -1. Okay. So if A remains -1, I directly print my answer. Okay. I don't need to do anything. It is already cool. If A is not -1, then I need to perform the step two. Okay. So here I would do the step two, which is joining these components. Okay. These components get joined with this. Okay. So we take these two nodes and join this component. Okay. Then we take these two nodes and join this component. So what I would do is, this is my A. Okay. The B I take is the node adjacent to A. Okay. So the B I take it the no in the adjacency list of A, whatever is the first value. Okay. It would have only one value. I know, because if it had more than one value, it is already removed. So whatever is adjacency A dot begin, whatever is the only node connected to it, that I would take it as B. So this is A, this is B. My A and B are done. And in C, I would take one by one, take every node from all the remaining components. So this is taken as C. Okay. So one by one, I would go to every value in my set that I would take as C. I perform the operation. Now, after the operation, this gets joined, this gets joined, this gets removed. Okay. So this would happen. Now, this became a single component. Now, when I need to add the next component, if I take the same A and B, and in this, if I add the node, it would form a cycle. So I don't have to take this A and B, but I have to take this A and B. Okay. So that's previous C becomes my new B now. Okay. So the previous C becomes my new B. Now we take these two nodes and join it with the next node of the next component. Okay. So my previous C becomes the B and they get joined. Okay. This is the new C. They get joined. This gets removed. Okay. This C becomes the new B. Okay. They get joined. This gets removed. That's what it would happen. So I would go to every value in my set. This would be represented by C. I perform the operation A, B, C, and B becomes my new C. Okay. So my like the C becomes my new B. Okay. So B equal to C. So whatever was the value of C, that would be the new value of B for the next operation. Okay. So that's what I just did. Okay. In my answer, I push back ABC. Now I could have performed this operation after pushing back. Okay. These changes also could have been done. Okay. But I did not do here because finally I only have to print the answer. I don't have to print the changed graph completely, the adjacency list of that. So I know that after all these operations are performed, my final tree, I would get a tree finally. Okay, I would get the cool graph. So performing those operations was not necessary. You could have done that, but I don't need to finally print that. Okay, so that need not be, my adjacency list need not be correct finally. But here performing the operation was necessary because after that I need to know for step 2, my graph should be updated, because if my graph is not updated, then I would get a wrong answer in my step 2. So after step 1, my graph should have been updated. But after step 2, I know my final answer is the answer that I get in my this. So my graph need not be updated. Okay. So I just perform these operations. I know all the components are now connected. It is a tree now. Okay, either it is a tree, or if A was equal to -1, it was a graph with no edges. Okay, then I would just print the answer. Whatever is the size of answer, that I would print. Okay, the size of my answer. And then I would go to every answer and print that V. Like V is a vector actually. I should run another loop and print this vector, but I have overloaded this. Okay, like I've overloaded my cout to print a vector with space separated. That's why it is like that. But technically, I should write it like this if you are not able to understand this. Okay. Instead of directly printing v, I should write for int j vij. Okay. So I hope now it is fine. For every vector in my answer, okay, it is a vector of size 3 containing ABC. So I print from 0 to 3, I run a loop and print vj. So ABC I printed space separated, and then I see out next time. Okay. So all the values in my answer vector are printed like this. Okay. I hope it is clear to you. Okay. This would be then, I think something I wrote wrong. Okay. So I hope this problem is clear to you. If you look at the time complexity, then these insertions are taking log of what can be the size of the list. At max n values can be there. So log n. Okay. This is done m times. So this is overall m log n. Okay. This updating the adjacency list. This is order of 1. This assign is order of n, and those clear. Okay. Now in this DFS overall, we are going to every node and performing an operation for at max all the childs. Okay. So for every edge at max, we would perform an operation for every edge. So for every edge, I do this insert and erase 6 times. Okay. So these are like log n operations, which are done for like 6 times. Okay. 6 into log n. This is done at max for every node. Okay. So its time complexity would be m is all the nodes. Okay. So DFS takes n plus m time. Okay. Either you go to all the nodes or all the edges. N plus m is the complexity for DFS. In that, extra thing we are doing is that for every, at max for every edge, we are erasing this. So 6 times log n is done extra there. So into log n is done extra here. So this I can say not for this overall. overall this time it would take. Okay, going to every node, if it is not visited, visiting it, and doing those operations in login time. So in this much time, this is done. Now step 1 is done. Then I go to every node in my set and find the first value and erase it. Erase would take login, but this is done only one time. Okay, so at max, I'm going to every value in my set. At max, there would be n values in my set. Okay, so n, and this one erase operation is done. So n plus login would be order of n only. Now in step 2, what I'm doing is I'm going to every value in the set, pushing back my answer. So this is order of the size of the set time only, and the size of the set is at max n. So this is order of n again. Okay. And printing this is order of my answer. Answer would be at max n, like n 2 times n plus m. Okay. So at max n plus m times. Okay. So overall complexity, if you look, so this was m log n, this was n plus m log n. Okay, these were n plus m. So overall, I can say my time complexity is order of n plus m times log n. So this would be well accepted for the given constraints of n and m up till 1e5. Okay. Space complexity would again be like we are using an adjacency list of size n plus m, like at max n plus m only would be the space complexity. There are m edges and nodes. So I hope this problem is clear to you. We can move to the next problem now. Okay, next is the problem E, common generator. So here you are given two integers x and y. We will say that x is a generator of y if and only if x can be transformed to y by performing the following operation some number of times, possibly 0. Okay, choose a divisor d of x, then increase x by d. For example, 3 is generator of, okay, so what we are given that x is called the generator of x, like x is called generator of y if x can be transformed to y by performing some type of operation. So 3 is a generator of x. What you would do, choose a divisor d and increase x by d. So 3 is one of the divisor of 3. So increase 3 by 3, make it 6. Okay. For 6, 2 is one of the divisor of 6. So increase 6 by 2, make it 8. So from 3, we were able to form 8. So we would say 3 is a generator of 8. Same way like this. Okay. Now Kevin gives you an array A consisting of n pairwise distinct integers. You have to find an integer x such that for each I from 1 to n, x is generator of AI or determine that such an integer does not exist. So you need to find such an integer x which is greater than equal to 2 so that all the values in the array, okay, all the values in the array AI, okay, so x is a generator of all the values in the array basically. So you need to determine such an integer x so that from that x as the starting point, you can form all the values in the array through some way by these operations. Okay, so this is the question. Let's take this test case. So what the problem is, this is n, you are given an array and you need to find such an x so that if you start with that x, you can form 8. If you start with that x, you can also form 9, you can also form 10. Okay, so here the answer was x equal to 2. Let's see how. If you start with 2, okay, you pick any divisor of 2. Okay, so for 2, its divisors are only 2, like greater than equal. So any divisor greater than equal to 2. So for 2, its divisors are only 2. Okay, it has 1 and 2, so 1 is not greater than 2. So excluding 1, it has only 2 as its divisor. So you can perform only one operation, which is with d equal to 2. You do 2 plus 2, make it 4. Now for 4, if you look at 4, it has divisors 2 and 4. Okay. So either you can take d equal to 2 and make it 8, or you can take d equal to 4 and make it 6. So 4 plus 2 is 6 and 4 plus 4 is 8. Okay, so these are the two possible cases. Then again with 6, you can its divisor are 2, 3, and 6. So you can perform any operation. So with 6, let's say you take d is equal to 3, you make it 9. Or if you take d equal to 2, you make it 8. Okay. And from 8, if you take d equal to 2, you make 10. So you can see all these 8, 9, 10, they are formed through some way starting with 2. So 8, 9, 10 all can be formed starting with 2. So 2 is a valid answer. In this test case, you can see 2 is a valid answer. So you need to find such an x. How can you do that? If you are not able to find such an x, you would print -1. For this case, it was not possible, so you print a -1. So how can you do that? Okay, just a second. So what you can observe here is, if you start with 2, let's say, to what values you can go if you start with 2? Okay, if you start with 2, the only possible option you have is take d equal to 2 and go to 4. Okay, no other possible option here. Now, after 4, you have two options. Take d equal to 2 and go to 6, or take d is equal to 4 and go to 8. Okay, you can also reach 8 from 6 if you take d equal to 2. So through that also you can reach 8, and through here also you can reach 8. So 8 is possible. Now with 6, you can take d is equal to 3 and reach 9 also. Okay. And then from 9, again, it has divisors of 3 and 9. Okay. So you can take d equal to 3, go to 12. Likewise. And from 8, it has 2, 4, and 8. You can take d equal to 2, go to 10. So what you can observe, if you start with 2, always whenever you do a plus 2, you can just do plus 2, plus 2, plus 2 and go to all even integers. That would be covered. All even integers are covered. From 2, you can always do plus 2, plus 2, plus 2 and go to all even integers. Because when you do a plus 2, if 2 was a, if it was an even integer, when you do plus 2, it would remain even. When you do plus 2, it would remain even. For even integers, 2 would be one of the divisors. You can always add plus 2. So this is one thing. Now, what other values can you cover? From 6, you take t equal to 3 and cover 9. Now, once you have got to this 6, you can take d equal to 3. So you can move in the multiples of 3, 6, then 9, then 12, then you can move 15, 18. All the multiples of 3 would be covered. Now, what about other multiples? So all multiples of 2 are covered. So for 2, all multiples of 2 are covered. For 3, except 3, this 3 was not covered. From 2, you directly move to 4. 3 did not came. So except 3, all multiples of 3 like 6, 9, 12, they were covered. Okay. Then next prime number is 5. So next there would be 5, 10. 10 is covered because it is multiple of 2. 15, it is covered because it is multiple of 3. 20, it is covered because it is multiple of 2. So again, like 5 and then 25, these would be the numbers that would remain. So when would they be covered is 5 would not be covered here. You can see from 4 we move to 6. So 5 is the number remaining here. But when you move to 10, okay, from here when you move to 10, now this 10 has 5 as a factor. So now all the multiples of here, you can use d equal to 5, make it 15. Use d equal to 5, make it 20. Okay. And then make it 25. So from 10, all the multiples of 5 are covered. So among the multiples of 5, this 5 was not covered, but from 10, 15, 20, all of them were covered. Okay. If you look at 7, here you can see that after 6, we move to 9, we move to 8, but we cannot move to 7 in any way. So this 7 is not covered, but the next multiple, which is 14, okay, it is a even integer. So again, from 10, we move to 12, we move to 14. So 14 would be covered. Once 14 is covered, it has 7 as its factor. So all 21, 28, all of them would be covered. So from 7, we can say that 7 is not covered, but 14, 21, 28, all are covered. So what you can notice here is if you take any prime number p, okay, then other than 2, okay, if you start with 2, I'm talking about the case when I'm starting with 2, when I fix x equal to 2. That is the case I'm talking about. So all even integers are covered, including 2. Among multiples of 3, except 3, all other multiples of 3 are covered. Except 5, all multiples of 5 are covered. Except 7, all multiples of 7 are covered. That means for any prime number p, except p, all other multiples of p are covered. Okay. So because after p, you have a 2p. 2p would have, now 2p would be an even integer that would be definitely covered. Once 2p is covered, it has p as a factor. Once it has p as a factor, all 3p, 4p, and 5p, they would be covered. So with this, I know if I choose, okay, so for x equal to 2, if I choose x equal to 2, then what all values can it cover? All values except prime numbers greater than 2. All values except prime numbers greater than 2 are covered. That you can write. So only the prime numbers, all the prime numbers except 2, all prime numbers greater than 2, they would be not covered. So like you can see this 3, 5, 7, 11, 13, they would be not covered. Like another proof I can say that why they would definitely be not covered is whenever you perform an operation, let's say you start with some value x and you perform an operation. What you do, you pick a divisor of x, okay, and then it becomes x plus d. Now you know that d is a divisor here. D is a divisor of x, and then you add a d. So for x plus d also, d is a divisor. Okay. If you have a number x which has a divisor d, so d is one of the factors of x, then when you add d to that, d would still remain a factor of x. Okay. If it was there, that you know. So whenever you perform an operation, so after one operation, if it was not the starting value, after one operation, you know that this number would have at least one factor, which would be d, and this d is greater than equal to 2. So this number definitely would have a factor greater than equal to 2, and that value is not x plus d. Okay, so that value. So d is a value is greater than equal to 2 and it is not equal to x plus d. So that means this number is a composite number. You know that this number has a factor d which is not 1, neither equal to the number itself. So if it was a prime number, it only has factors 1 and the number p itself. But it has some other factor, that means definitely this is a composite number. So that means we can say that after performing any operation, we would only get composite numbers. So the prime number can only be obtained if it is the starting value. So what we conclude that prime numbers can only be generated if we start with x is equal to p, x with that prime number only. Okay. Otherwise, it won't be generated. So if we have some prime numbers 2, 3, 5, 7. Okay. So either we would start with x equal to 2. In that case, 3, 5, 7, they won't be generated. Or if you start with x equal to 3, in that case, 2, 5, 7, they want to be generated. We know for sure. That means we cannot have more than one prime number in our array. If we have more than one prime number in our array, we know that either we would set x equal to 2, then 3 can't be generated, or we would set x equal to 3, then 2 can't be generated. Because to generate a prime number, it can only be generated if that is the starting value. So we would have only one starting value, x. Okay. X cannot be equal to both 2 and 3. Either it would be 2 or it would be 3. So if we take it 2, then 3 won't be generated. If we take it 3, then 2 won't be generated. So that means if more than one value in the array A is prime, then we print a -1. Okay. And if we don't have any prime value, okay, if no value is prime, okay, then what we can see, that we can see this case when we took x is equal to 2. Okay, when we took x is equal to 2, we got all the values except, okay, so by taking 2 we got all values except prime numbers. So if we only have composite numbers, by taking x equal to 2, all composite numbers are covered. So we can say that if we have only composite numbers, one possible answer is x is equal to 2. So just print that answer. Okay, we just need to print any one possible answer. So by taking x equal to 2, that answer can be printed easily. So if more than one prime number is there, our answer is definitely -1. If no prime number is there, answer is x equal to 2. Okay, now the only case remaining, if there is one prime number and that prime number is p, let's say. Okay, now definitely for this case, either our answer would be p itself, because in order to generate p, we would need to set x is equal to p. So for this case, either our answer would be x equal to p or it would be -1. So we just need to check whether taking x equal to p, we can generate all the numbers in the array or not. If not, then we print -1. If yes, then we print p. That's the only thing we need to check. So check if with x equal to p, can we generate all numbers in the array? Okay, that's what the only thing we need to check. If yes, if the answer is yes, then we print p as our answer. If this is no, then we print -1 as our answer. If all the numbers cannot be generated with x equal to p, we print -1. If all the numbers can be generated, that with x equal to p, yes, we can generate all the numbers. Okay, we cannot pick x anything other than p, because if we are picking anything other than p, then this p would not be generated. Okay, so now how can we check with x equal to p, what all numbers can be created? Like, can all the numbers be created? Okay, now for x equal to 2, we know if p was like, if p was equal to 2, if 2 was the only prime number, then we know, like, we can generate all numbers except the prime numbers, and we know there are no prime number existing. 2 is the only prime number, because if there was more than one prime number, we have already printed -1 here. If there was more than one value which was prime, we already have printed -1. So if there is only one value which is prime, which is 2, then all the other values are composite, then we can just definitely say yes, that all the composite values can be done. So we print 2 as our answer. Now for other cases, let's say p is 3. What all values can be generated? Can we generate all the values? Okay. So we start with x equal to 3. Then for 3. Okay. So for any prime number, the first thing is it has only one divisor, which is the number itself. So only d we can pick is d is equal to 3 and move to 6. So from p, we would move to 2p for any prime number. Okay, so all the numbers in between p and 2p, they won't be generated for sure. Okay, so if any number between 3 and 6 is existing in my array, then I print a -1. It cannot be found. Okay, now what about after 6? After 6, okay, we started with x equal to p. So p was the only divisor of that prime number, and we moved to 2p. Now for 2p, we know 2 is one of the factor. Okay, so we can pick D is equal to 2 now, and go to all the multiples of 2. So all even numbers after 2p are covered. That's one thing. Okay, so like for this 6, 8, 10, 12, all the even numbers are covered. Okay. What about the other numbers? Now, with 3, I know all the multiples of 3 would also be covered. So 3, 6, and then 9, and then 12, they would also be covered. Okay. So all multiples of 2 covered, 3 covered, which all would be not covered. Now, after 2 and 3, we have 5. Okay. Are the multiples of 5 covered? Let's see. We have a 5, and then now 5 is not covered for sure because it lies before 6. After 6, there is a 10. Okay. So 5 into 2, 10. So 10 is a multiple of 5, which is covered here. So once 10 is covered, it has a factor 5. All the multiples of 5 would also be covered after 10. Okay. So we can say that 5 is not covered here, but all the other multiples of 5 like 10, 15, and 20, they are covered here. Let's see for 7. For 7, you can see this after 6, we get to 8. We cannot form 7 directly. Okay. You know, the prime number won't be covered, obviously. But after 7, we have 14. Now this 14 would be covered here. So from 14, we can cover all the multiples of 7. So all the multiples of 7 also are covered except 14. So like for x equal to 3, you can see like other than this 4 and 5, all numbers from 6 are covered except the prime numbers. It would be the same case like 2. Okay, what if we have some bigger prime number? Okay, let's see for x is equal to 11. Okay, from 11 we get to 22. So all the numbers in between won't be covered. Now after 22, we can pick 2 and go to all the even numbers. That is okay. Okay. But from 24, we can also move to this 24 has factors 2 and 3. Okay, 3 is also one of the factors of 24. So from 24, we can move to all the multiples of 3 like 27, 30. They would be covered. All the multiples of 3 would be covered from 24. But before 24, multiples of 3 are not covered. Then if we look at 25, here 25 is not covered from 11. 25 is not covered because after 24 we move to 26. From 22 we need to add a plus 3 to move to 25, but 22 doesn't have 3 as a factor. It only have 2 and 11 as a factor. Okay, so from 22 you can move to multiples of 11 or multiples of 2. So I move to 24. So you won't move to 23, which was prime, as you know. And from 24 you won't move to 25 because you can never have plus 1. D cannot be 1. So basically 25 won't be covered. But after 25, the next multiple of 5 is 30. Would 30 be covered? Yes, because 30 is an even number. After 24, all the even numbers 28, 30, they would be covered. So once 30 is covered, okay, so once 30 is covered, all ahead of that, the multiples of 5, they would be easily covered. Okay, so here for x equal to 11, we can say that for multiples of 2, starting with 22, all the multiples of 2 were covered. 22, 24 from that. For 3, the multiples of 3 starting with 24 were covered. Multiples of 3 starting with 24 were covered. Before that, they are not covered. For 5, 25 was not covered. 25 was not covered, but from 30, all the multiples were covered. From 30, all the multiples were covered. What about 7? 7 won't be covered, obviously. 14 lies in this range, won't be covered. 21 lies in this range, won't be covered. 28, the first value after 22 is 28. Whether it would be covered? Yes, it is even after 24, so it would be covered. Okay, so like after 2 into p, so after 2p, all the even numbers are covered, and before 2p, no number is covered except 11. So I can say that before 2p, if you are in this range, then no number is covered, and after this range, all even numbers are covered. Okay. So for any multiple of for any prime number 7, we can say the first multiple of 7 that is covered. What is that? Okay, that is the first value after 2p, which is even. That would be the first multiple of 7 which is covered. So after 22, what is the first even multiple of 7? It is 28. Okay, so we can say that from 28, all multiples of 7 would be covered. So 28, 35, 42, all would be covered. For 5, what was the case? For 5, the multiple of 5 just above 22 was 25, but that was not even, so that is not covered. But 30, it was even, so that is covered. So I can say that for any prime number p, like we take x, if you start with x is equal to p, so p is the prime number through which we are starting. Then for any other prime number, let's say p naught, this would be covered if starting from first even multiple of p naught after 2p. Okay. From that, all multiples of p naught would be covered. Starting from the first even multiple of p naught, all multiples of p would be covered. Like 7. Starting from the first multiple of 7, first even multiple of 7 after p, it was 28. So from 28, all multiples of 7 are covered. 28, 35, 42, they are all covered. Okay. So what we can say that if we are taking x is equal to p, okay, whether a value AI would be covered or not, that would be decided if first I would find out where this AI lies. Okay. If this AI is less than 2p, then definitely it is not covered. Okay. Because less than 2p, you can see less than 2p, no number is covered except if it is equal to p. Okay. So we are ignoring p here. Okay. If it is the prime number only, p, then obviously that is covered because x is only p. But other than that, other than p, all numbers less than 2p, they are not covered. So if AI is less than 2p, it is not covered. Now, if AI is greater than 2p, what we would do is we take the smallest prime factor of AI. Okay, so for any number, if you want to check whether it is covered or not, it is a multiple of some smallest prime factor. Okay, so if we want to check for 28, okay, or if you want to check for 35, how would we check for 35? The smallest prime factor of 35 is 5. Okay, it has prime factors 5 and 7. These are its prime factors. Smallest prime factor is 5. So we would check if the multiples of 5 are covered or not for 35. So for multiples of 5, we would check yes, 35 is covered. So we would answer it is covered. So for any AI, we say that, let's say the SPF of I is Y. Okay, let's say the smallest prime factor of AI is Y. So we would check whether the multiples of Y are covered or not for AI. So we know that this AI is now, it's not less than 2p, it is greater than equal to 2p. So if it is even, one more case, if it is even, all even numbers are covered. So if this AI modulo 2 is 0, okay, so else if it is even, then it is covered. And in the else case, I'm taking the condition. Okay, all even numbers above 2p are covered. This thing we concluded. Before 2p, no numbers are covered. Above 2p, all even numbers are covered. Now the remaining numbers, the odd numbers above 2p, for that we need to check their SPF. Okay, we need to check if their SPF is Y. Now we would need to check whether the multiples of Y are covered or not. Now Y is basically the P naught here. So we would check if the multiples of Y is covered or not. For that, which is the first even multiple of P naught after 2P that is covered. So what is that? So basically, we would check if AI is an multiple of Y after 2P. Okay. So if AI is an odd multiple of y, then and it is the first odd multiple of y, then it won't be covered. Otherwise, it would be covered. Like for 5. For 5, all the multiples of 5 above 2p were 25, 30, 35, and all. Okay. The first multiple of 5 above 2p was 25, which was odd. So it was not covered. But after that, we got an even multiple. So all other multiples got covered. So here, this was odd. So it was not covered. So we would check whether this is an odd multiple of 5 and it is the first odd multiple of 5 after 2p, then it won't be covered. So we would check if, so what multiple of, if we divide AI by y. Okay, so here if AI was 25, to 25 by 5, we got that it is the fifth multiple of 5. That means it is an odd multiple of 5. Okay, it was a fifth multiple of 5, not an even multiple. If it would have been even multiple, then it is even already. Like here only it would be covered. So it is odd definitely. This is odd definitely. It is an odd multiple only. Now we would check whether it is the first odd multiple. So if it is first odd multiple, then this AI by y. So like if from, or you can say that if from AI, if you subtract y, okay, then if it was the first odd multiple of 5, then from that, when you subtract 5, you get 20. This would be less than 2p. Okay. So if it was the first odd multiple, then if in that you do -5, it would become 20, which is less than 2p, which was 22. Then it was odd multiple. But if it was 35, then from 35, if you do -5, you get 30, which was greater than 2p. So it was not the first odd multiple. So if from AI, you subtract y and that becomes less than 2p, then you say that no. This is the first odd multiple. It cannot be formed. Else, you say it is fine. Okay. So now this is the way you check whether AI can be formed using x is equal to p or not. So using x equal to p, can you form AI or not? This is how you check. So either this some value, this AI, if it is less than 2p, you cannot form. If it is greater than equal to 2p and it is even, then you can form. Now, if it is greater than 2p and it is odd, then you take the SPF of AI, and if AI minus that SPF, okay, so if it is the first odd multiple of y, then subtracting that y would make it less than 2p. Okay, so if it was the first odd multiple of y, that means AI minus y is less than 2p, then you say no, otherwise you say yes. Okay, I hope this logic is clear to you. So now we can look at the code. So here the first thing, in order to compute SPF, we would pre-compute it like before entering our t-test cases only. I run a sieve for n. My AI was given up till range of AI was 4 into 10 to the power 5. So I need to compute my SPF until 4 into 4e5. Okay, 4 into 10 to the power 5. So till there I run a sieve. Okay, in my sieve function, I pre-compute my SPF, vector int SPF, SPF dot assign this, and you know the normal initialize SPF I as I and run a sieve function to calculate your SPF. This way I have computed my smallest prime factor, the SPF, using this sieve. Okay, once that is done, once that pre-computation is done, I enter every test case and my SPF is already calculated. Okay. Now I take this input array n and the input array of size n. This input part is done. After that, I initialize p is equal to -1. Okay. I would check in my array whether I have a prime number or not. So a number is prime if its SPF is equal to itself. That's the way to check a prime number. So in the sieve, I only constructed the SPF array. Through the SPF array, we can easily check whether the number is prime like this. So if the number is prime and we have already not got a prime, then I assign that I to P. And if we have already got a prime, if one of the number is already prime and we get a second prime number, then I see out -1 and return. But if we have two prime numbers in the array, definitely we would have -1 as the answer. We cannot form two prime numbers. Okay, so if p was not equal to -1, we already had a prime number and we again got a prime number, we print -1. And we didn't have a prime number. This was the first time we got it. Then we take p is equal to I. We take that. Now, if p was -1, it means we never got a prime number. Or if p was 2, it means 2 is the prime number present. That means all remaining numbers are composite, and with x equal to 2, we can always form all the composite numbers. So we print 2 as our answer and return. Okay. So this case, I hope that I wrote here. If we have more than one value in A which is prime, we print -1. Okay. So here, if more than one value was prime, we print -1 directly. Okay. And if no value is prime, we print x equal to 2. Okay. So if no value is prime, we print x equal to 2. And then if the prime number is 2, okay. So then if the prime number is 2, then we would have yes as our answer. That means I would print x is equal to p. So for if 2 is the prime number, or if there is no prime number, 2 would be our answer. We return. Now for all other prime numbers, we would have to check. So we'll check every element in the array. Now we know we got a p. Whichever is the prime number, we take x is equal to p. We take that only as our x. Okay, we take that only as our starting value. So with p as our starting value, we need to check whether for any value we can form that or not. Okay, so how do we check? So for any AI, if it is less than equal to 2, if it is less than 2p, then we say no, we cannot form. So if I is p, we continue. So if we are at p, that can be formed, obviously, we know. For all the other values, if I is less than 2p, okay, and it is not p, okay. So for all values less than 2p, we print a -1 that we cannot form. So I is actually AI for all values in A. So if AI was less than 2p, we print -1. Now, if AI was an even number, then it was okay. Greater than p and it was even, then we do continue. Okay, let's check the next number. Okay, here only we cannot say -1. Okay. Else we take the SPF of AI. So y is the SPF of AI. Here I have taken x as the SPF of I. Okay. So we take the SPF of AI and we check if AI minus y is less than 2p. So if I minus x is less than 2p. Okay. Here AI is I and y is x in my code. Okay. So I minus x is less than 2p. This condition is written. If it is the case, then we print -1 that we cannot form. Okay. And we return. Otherwise, we just do continue that. Else, that is fine. Let's check the next number. Okay, so in else we are not writing. Anyways, we'll go to the next value in the loop. So if at any point we didn't print a -1 and returned, then we print p. That if it's all the values satisfies the conditions, all the values are okay, they are contained, that p would be my answer. Okay, I hope this is clear to you. What would be its time complexity? This input part is taking order of n time. Now you're going to every element in your array and you just check this is order of one thing done. So this is order of n. This is also order of 1 constant time. Here you are going to every element in the array. This is if else. Okay, all are order of 1 operations. So this is again order of n only. Okay, and we see out p. So overall my time complexity would be this sieve. Okay, this sieve n is running an order of n log of n times. Okay, so like overall you can say the n, basically you can say this is 4e5. Okay, the AI, the maximum AI that you are given. Okay, so 4e5 log of 4e5. Okay, this constant thing, this is the time complexity for sieve plus our order of n for every test case. Okay, so order of the sum of n for every test case is 1e5 only. Okay, so basically this would be 4e5 into some very small constant. At max it would be 1e6, plus 1e5. Okay. At max, it would be a 1e6 only. So that would be well accepted. And my space complexity would be, I'm using a sieve. In that, I'm storing this SPF, which is taking a size of 4e5. So that would be our space complexity, size of 4e5 for the sieve. And then array of size n is taken here. N would be smaller. So this is my time and space complexity. I hope this problem is clear to you. Okay, doing the maths was the main thing. Understanding it in terms of multiples of prime numbers. Analyzing this was the main thing here. Okay, I hope it's clear to you. Thank you very much for watching. Goodbye.